So now let's look at how we will solve logarithm equations. As I mentioned earlier, the easiest type of logarithm equations to solve are those where you can apply the one-to-one property. All that means is you have the log base A of some argument x equal to log base A of another argument. We'll call it y. When these two logs match up and there's nothing else on each side, then you can just drop the logarithms and solve for x equal y. So I've got these two equations set up where we can use the one-to-one property. I kind of call it the log equal log property. Take a look at this first one. I've got ln of 3x plus 2 equal ln 4x. I've got a single log on the left, a single log on the right. They're the same base, so I can apply this property, which says I can just drop those logarithms and solve for the two arguments equal to each other. So all I need to do is solve for 3x plus 2 equal 4x. That's a simple linear equation. We can bring the 4x on this side, bring the 2 on the other, to get 3x minus 4x equal negative 2. So negative x equal negative 2. And if I divide by negative 1, I get x equal 2. And you can plug that in and check it. 3 times 2 is 6, plus 2 is 8. So ln 8 is equal to 4 times 2, which is 8. So ln 8 is equal to ln 8. It works. This next one, we're going to have to do something with it first before I can apply this one-to-one property, because I don't have a single log on the left equal to a single log on the right. I got a single log on the right, but it's the left part that I'm going to have to condense into a single logarithm before I can apply this property, this one-to-one property. Remember earlier from section 5.3, if I had two logs that were added, then I could combine those two logarithms using multiplication. So I can condense these two logarithms into log base 5 of x times x plus 1, multiplying those two arguments. Remember, addition turns into multiplication. Now I can apply the one-to-one property because I have the log of a single value or a single argument equal to the log of a single argument. So log equal log means I can just drop those and solve for what's left. X times x plus 1 equal to 20. So by dropping those two logarithms, I'm left with a quadratic that I need to solve. So let's get all our terms on the left. X squared plus x minus 20 equals 0. I believe this one's going to factor x plus 5, x minus 4. Negative 20, positive 1. Okay, and then once we have it factored, we set them to 0. And we get a solution of negative 5 and a solution of 4. But we have to always check our solutions, because it is possible that by putting one or both of those back into the original for the variable x, we could end up taking the log of a negative number, and that's impossible. So notice over here when I checked x equal 2, it worked out great. Let's check each of these. So what would happen if I put a negative 5 for that x and a negative 5 for that x? I would end up taking the log of a negative number. which is impossible because of the domain of a logarithm. So by looking and inspecting x equal -5, I see that one won't work because I end up taking the log of a negative number. Okay, so he's out. Let's check the next one. Let's put in a 4. 4 and a 4. Do I end up taking the log of a negative number? Would I put a 4 in place for x? Well, this would be log base 5 of 4. Check. Log base 5 of 5. Check. This one is okay. So even though we came up with 2 answers, by checking there is only one solution, which is x equal 4. This is a very important step in working with logarithms. Always go back and check your answers. Necessary to go back and check your answers into the original equation. Okay, so this was using the one-to-one property when it's in the form of a log equal to a log, or it can be put into the form of a log equal to a log. But what if it doesn't fall in that category? Well, if you can't put it in the form of a log equal to a log, then we will use the next approach by converting a logarithm to the form a to the y equal x. Remember, we did that earlier, converting forms from logarithm form to exponent form, where we just take this a, set it to that y power, and then equal to x. Sometimes I refer to it as bringing it full circle. But I can't bring it full circle until the log stands alone. I have to have a logarithm of one thing equal to one thing on the other side. So in other words, this logarithm needs to stand alone. And he doesn't because he has a +5. So I would have to get that logarithm to stand alone by subtracting 5 on that side. This logarithm does not stand alone. I'd have to get rid of the 2. How do I get rid of the 2? I would have to divide by 2 on both sides. And notice these logs don't stand alone. There's actually 2 logarithms. So I would have to actually condense this into a single logarithm before I could do anything. And condensing that addition becomes multiplication. So I need to have my logarithm standing alone. Log base 4 of x minus 7 equal 10. ln 3x equal 2. Log of x times x minus 3 equal 1. Notice in each one of those equations, the log stands alone, the log stands alone, the log stands alone. And there's only one logarithm. There's not a log on both sides. So I've got one logarithm in my problem, or in this case I had 2, but I condensed it into 1. I don't have a logarithm on the right-hand side. That's going to tell me to use this property where I bring it full circle, which means, let me go with a different color here. Let's go with the green. Which means I take this base 4, raise it to this power 10, and set it equal to that argument. This base of e, raise it to the second power, set it equal to that argument. This base of 10, raise it to the first power, set it equal to that argument. Let's see what that looks like. 4 to the 10th equal x minus 7. E to the second equal 3x. 10 to the first power equal x times x minus 3. So look at the way we have to work with these logarithms when I don't have a log equal to a log. We have to get that log to stand alone or condense it into a single logarithm. So we want a single log, and then we're just going to bring it full circle. That base to this power equal to the argument. Base to the power equal to the argument. Base, that power equal to that argument. Now, there's no logs. We can solve these. So to solve this for x, all I need to do is add 7. So 4 to the 10th power plus 7. And we can figure that out. 4 to the 10th power plus 7. 104,853. 104,853. There is our value of x. 4 to the 10th plus 7. Make sure I did that right. Sure. Okay, how do I solve this one for x? Divide by 3. And I'll have x equal e squared over 3. This would be the exact answer, but if I wanted a decimal approximation, I would take e, square it, then divide it by 3. So here is e. I'm going to square it, then I'm going to divide it by 3. 2.463. So this would be the decimal approximation, and this would be the exact. Well, this guy turns into our lovely quadratic. I'll have 10 equal x squared minus 3x. Well, quadratic, let's get all terms on one side. This one is going to factor. 10 is 5 times 2, negative 5, positive 2. Set equal to 0. And we get 2 solutions. But we have to check them. We have to check them back into the original problem. And I made a mistake because that's a negative 2. So x equal 5, x equal negative 2. If I put 5 in the original problem for my x, I end up taking the log of 5 and the log of 5 minus 3, which is 2. I'm okay because I'm not taking the log of a negative number. X equal to 5 is good. Let's plug in a negative 2 for x. So let's replace the x's with a negative 2. So I'll have the log of negative 2 plus the log of negative 2 minus 3. That means I'm taking the log of a negative number. Log of negative 2 is the log of a negative number. This guy doesn't work, so he is not part of the solution set. Only x equal to 5 would be our solution. Let's check out an application. Remember back in 5.1 when we worked with exponential functions, we saw those banking problems where we had, if we invested an amount and it was compounded continuously, we used this formula. Well, here's what we want to do. I'm going to invest $4,500 into an account. 4,500 represents my P. It's compounded continuously, and I want to find out the time required. So the time is an exponent. I want to find the time required for my amount to double and triple if my interest rate is 0.0465. Let's just kind of get this set up. P is 4,500. The rate is 0.0465. and that's times t. And we want to solve for t, and t is in an exponent position. Another part of this is how much time, what is that value of t going to be for my investment to double? So let's take a look at this. If I'm investing $4,500, how much is that if I doubled it? It would be $9,000. That goes in place for A because A is the amount in the account after all that time has passed. So to figure out how much time required for that account to double, what I'll do is double 4,500. So I'll have 9,000 equal to 4,500 times e to the 0.0465 t power. That's the equation I have to work with, and that's the equation I need to solve for t. So it's an exponential equation. So let's back up to exponential equations. I can't use the one-to-one property because I don't have the same base on each side. So I'm going to have to go about it another way, which is to isolate the exponent term and take the log of both sides. So I need to get this exponent term by himself. I want him to stand alone so I can take the log of both sides. So to get him to stand alone, we're going to divide both sides by 4,500. Go back to green. Well, what's 9,000 divided by 4,500? We should get 2 because we're seeing how long it takes to double. So I have 2 equal to e to the 0.0465 t power. Now that my exponent term stands alone, my procedure says just take the log of both sides. And I'm going to ln both sides because the base there is an e. So ln base e of e means all that cancels, and I'm left with 0.0465 t. Remember, when the bases match, they cancel out. That's equal to ln 2. So how do I solve it for t? Well, since it's that amount times t, I'm just going to divide by that value to give me the time it would take for my investment to double. So let's check it out. It's going to be ln 2 divided by 0.0465. 14.9 years. So if I invested 4,500 in 14.9 years, I will have doubled my investment. So now I want you to pause it, follow what we did in this problem to determine the time it would take to triple your investment. So pause it, work it, and come back. Following what we did on the previous example, we should see that it would take 23.626 years for our investment to triple. You can follow the work that I did here. For tripling, I used 13,500 because that's 4,500 times 3. And when I divide by 4,500, I end up with a 3 on the left. Okay, let's look at this last application. Be sure to read the problem in its entirety before you try to work it and understand what the variables represent. Capital T is temperature. And what does little t stand for? It says it's somewhere, but it's time. Little t is time. And it represents the time that has elapsed since death. So read it again. It's asking us to estimate the time of death for this person based on the information that we've been given. So read through it, see what value you're going to put for capital T, which is temperature, and then work on calculating the time, and that's the number of hours that has elapsed since death. So figure out the time of death from that. So work on it. You may have a question regarding which temperature do I use? Do I use the one at 9 a.m. or the one at 11 a.m.? Using either one, you can use either one. You'll get the same answer if you realize what the time frame is. I use the temperature to be 85.7 degrees, which corresponded to 9 a.m. If I used the 82.8 degrees, then I would have to make myself a note that corresponded to 11 a.m. So when I plugged in the 85.7 for temperature into my function, I calculated it this way on my calculator. I come up with T equal to approximately 6 hours. So that means 6 hours had elapsed since death. So if I start at 9 and go back 6 hours, then that tells me the time of death was 3 a.m. And I apologize, I've got a dog barking in the background, but that's okay because we are done. Let me know if you have any questions.